5. Circuit troubleshooting. Troubleshooting is the process whereby you diagnose a malfunctioning system and identify the specific defect. Once the defect is identified, a judgment must be made regarding the feasibility of repair. And there are a number of considerations that have to be made. One is the time. How long will it take to repair this? Sometimes there are critical systems that there is not time to repair them, and you must simply replace the entire circuit board and just continue to use the system. So there is the time involved, and also there is the cost, because when you go to repair a system, there's going to be the wages of the person repairing it, the cost of the components to make it work, and so there's considerations need to be made. Is it going to cost more to fix this than simply to replace it? This chapter examines troubleshooting strategies and techniques. Troubleshooting is a lot of fun for those that, in fact, many people make a career out of doing this, and it can be a very rewarding career. People, in our electronics program at North Seattle, many students will go out into industry. They work in biomedical repair, some work in telecom, some work in broadband, industrial power, and for the most part they are maintaining and repairing electronic systems that we come to depend upon in our daily lives. Okay, troubleshooting series circuits. This particular section, 5.1, we're going to do it in two parts. And let's see, the first thing we're going to say is pure series circuits are rare in practical electronic systems. So you don't commonly see just a pure series circuits. However, what you will see is you'll see parts of circuits that are series within a given system, but usually the entire system isn't just a series circuit. But you do need to know how to troubleshoot them, because you will find series circuits within systems. Troubleshooting strategies applicable to series circuits play a major role in troubleshooting advanced circuit configurations. Logical troubleshooting procedures will aid in analyzing and troubleshooting all circuits, simple or complex. 3 goals as a troubleshooter should be. Okay, number 1, make a measurement only if you know what a good reading should be. And the idea here is that you can make all kinds of measurements, but if you don't know what the correct measurement should be, you're probably just wasting your time. Make as few measurements as possible, and the idea here is not to waste your time. And number 3, select the best tool for the task at hand. And typically electronic troubleshooting tools would be things like oscilloscopes, voltmeters, and then depending on the task, if you're out in the broadband industry, you'd probably want signal level meters. There's just a wide variety of tools out there that might be appropriate for given tasks. Now, know what is normal in a circuit, and there are a number of sources for getting this information. The first what we'll mention here is a schematic, and a schematic is just a printed readout of the circuit configuration, where you can look at each component on paper and view the overall circuit. This is one of the primary troubleshooting tools. Many times schematics will have voltages written in so that you'll know what you should read at specific points. Also, another good way to know what is normal is to have a known good circuit for comparison. And the idea here is that if I have say I've got a box here, and we'll call this the bad one, and here is the good one. And let's pretend that we have troubleshooting points or voltages that we are measuring, and we suspect that something is wrong here. We could measure the known good box and make a determination, well, is there something wrong or isn't there something wrong? And so a known good circuit is a good way to know what is normal in a given circuit. And then finally, there is simply intuitive understanding. And intuitive understanding usually comes with time. A given technician will be able to look at a box, look at it, and intuitively he'll have a sense of what is wrong. Oftentimes this is based upon experience. Okay, developing a solid intuitive understanding of circuit behavior is important to becoming a skilled troubleshooter. There are some general rules that form the basis for all troubleshooting efforts. The effects of defective power supplies, open circuits, short circuits, and components whose values have changed are important to understand. So first we're going to look at the effects of an open circuit. Open circuits are characterized by having infinite resistance. Okay, infinite resistance. So in this case we're considering resistance, and we're saying that open circuits will have infinite resistance. And in the circuit here we're looking at, here we have a component, and here we're showing a resistor here, and the resistor is open. Now, commonly, what will cause this is too much current has flowed through this circuit, and this particular component may have just disintegrated, burned up, and you look into your circuit and you just see simply a charred component there. And if you were to measure from test point 4 to test point 5 with an ohm meter, you would commonly expect to see infinite resistance, because this component ceases to exist because it's simply burned up. So this is typically, you would expect to see infinite resistance, but that won't always be the case, because sometimes when you measure the circuit, you think that you're measuring across here, but what actually is happening is the ohm meter doesn't know that you're just measuring across here. It may measure around like this, and you may get a resistance. It may be a rather high one, but it may not necessarily be infinite, because it may measure a different path through the circuit. An open circuit will appear to have the applied voltage across it. Now, one of the things that often surprise students is they go in and they measure. Now, this is when you're measuring voltage. When we measured resistance, the circuit was turned off. When we measure voltage, we have power applied. We go in and we measure test point 4 to test point 5, and rather than seeing 0 volts, we will see oftentimes in a case like this you might read 25 volts. And people wonder, well, why is that? Well, consider the fact that for when this circuit is operating correctly, we have current flowing through this circuit. We have that loop, which is a requirement for all circuits. Now, when this component opens, we no longer have that loop. So now there is no current flowing through these components, and you might notice the little 0 here on all these components indicating 0 volts. Well, why is there 0 volts? Well, let's remember Ohm's law. We said that voltage equals current times resistance. Now, the resistances have remained unchanged, but now the current is 0. So 0 times the resistance is going to equate to 0 volts. And so in this circuit, now there are no voltage drops across these components. And so what will happen is when I insert my meter into the circuit, I will measure the supply voltage, because there is no drops at any point in this circuit. Okay, if the open circuit appears between a monitored point and ground, the meter will read the source voltage, otherwise it will be 0. Okay, so that's just what we mentioned here. If usually when you're measuring something like this, you'll have your meter, and you'll have one probe going to ground, the other probe going over like so. And so in that situation, it's just what we just previously described, that in this case I would read the supply voltage. And as a note down here, if the circuit is open, how much current is flowing? None. How much voltage will be dropped across each resistor? 0. What voltage will be measured across the open? And that is the power supply voltage. Okay, effects of a short circuit. The previous screen we looked at the effects of an open. Now we're going to look at basically the same circuit, and we're going to look at what happens if we have a short. A short is characterized by having zero resistance or very low resistance. So again, if the circuit is turned off and we are measuring resistance, and we measure from this point to this point, we're going to measure and this is the case of a short, either a very low resistance or zero resistance. When a short circuit occurs within a series component, other components in the series will have higher currents. Okay, so in this entire circuit, we have maybe I'll put an RT here for the total resistance. Now remember that current equals voltage divided by resistance, right? And now if this component shorts, then the total resistance is going to decrease, and so the current in the circuit will increase. And you see these little blue arrows here, and they have a little V tied to them. This is indicating that the voltage across all of these components will suddenly be a little bit higher. Now the reason that the voltage is a little bit higher is because of this. One of the resistors has been removed, shorted across, so resistance has gone down, current has gone up, and so all the voltages have increased a little bit. When a short circuit occurs within a series component, other components in the series will have higher currents, which we just shown. The voltage across a short circuit is zero. So now this was measuring resistance. If we measure voltage, and we come in here and we place our little voltmeter in the circuit, and we measure from here to here, remember it is a short, we will measure 0 volts. The best tool for diagnosis is a VOM, and so with a VOM volt ohm meter you can measure the voltage and the ohms. And what do we got here? The resistance across R4 is 0 ohms. The voltage across R4 is 0 volts. The current through the short, current increases because R4 is out of the circuit, and we've mentioned all of that over here. Okay, this is that same schematic, and just as a review here, with R4 shorted, there will be an increase in current. The blue arrows indicate larger voltages across every component because of increased current. Therefore, the voltage read across every component will increase. Now that is, notice, therefore the voltage read across every component with respect to ground will measure closer to the applied voltage. I mention this because of in some summary statements in this chapter, they make mention of the fact that the voltages across every component will measure closer to the applied voltage. Now they won't measure the applied voltage, but since every voltage has increased, they will be closer to that applied voltage. Okay, in this section we introduced troubleshooting. We looked at the effects of a short circuit, and we looked at the effects of an open circuit. And we talked just briefly about intuitive troubleshooting, the goals of a troubleshooting, and what is normal in, or how to determine what is normal in a given circuit.